This is Code Dive, and our next speaker is Oleksii Pilkevych. Now, Oleksii is a student at Wroclaw University of Science and Technology and works at Nokia as Python developer for test automation. He loves sports and psychology and stand-up comedy, and if triggered, he can go on about prog metal bands on end, and he can talk about it until your head explodes. So his talk is called Async. Oh wait, Oleksii, so some prog metal references are fine, but explosions, well, maybe not today. Other than that, off you go.
I always wished I could drink coffee like that from the comfort of my own home on other code dives. Now, today we are going to talk about Async I/O, and I am going to present how I would like to have Async I/O taught to me when I was first starting out. So, if you are already an experienced programmer and experienced with Async I/O, this might be a little bit boring for you, but you still might find something interesting in the way I give my own spin to the basics of Async I/O. If you are a beginner, it should give you a solid foundation. So let's get started. There comes a time when you want to do a bunch of stuff at the same time. And when such need arises, you remember that, oh, there's this framework in Python I heard about. It's called Async I/O. So you go to the internet and you copy the first Hello World example. It goes something like this. You write a normal function with a little bit of weird syntax, and then you run it. Also, in a bit of a weird way. And that works. It prints hello, sleeps for 1 second, and prints goodbye. But you might notice it's not happening at the same time. So if you're like me, you think, aha, I need to have 2 of those. So you make another function and you decide to call the first one twice from it. So far, so good. Let's run it. Turns out it's still happening sequentially. So why is that? Because intuitively, when you look at this await, it kind of tells Python, okay, at this point, you are free to do whatever you want to do, and you can then come back to finish it later, right? Well, turns out no, because it's not happening at the same time. So then you go to the docs and you find out that what you have to do is you have to use some kind of Async I/O function to wrap those 2 coroutines into one awaitable object. And once you do that, using Async I/O gather, you can notice, finally, that it's happening at the same time. Now, honestly, the first time I did something like this, I thought, okay, this works nicely. The only problem I have is that I'm using some weird functions here. So why don't I just go ahead and do the sleep the way sleeps in Python are done. And when you run it, you may notice it's happening sequentially again. So why is that? You're using this gather function to wrap those two coroutines. This coroutine has a sync keyword here. Oh, maybe you can await. Ouch. Turns out you can't. So this is the point where everything becomes just a little bit harder. So in this case, let's go to the basics. Recently I had a chance to teach Python to my girlfriend, and after an hour of me blabbering about how Python is great, unbelievable and amazing, we reached this example program. Yeah. And after we wrote it, I thought, okay, that's the point where you usually start learning about ifs, loops, and all other bells and whistles. But I thought, have we really explored everything in this example? And I started trying to complicate it with all the knowledge we had at this point. And I ended up with this little program. Yep. So what's interesting about it is it's very simple, but when I showed it to my friends, who are, not all of them are Python programmers, but very often they would get confused and they wouldn't give the right answer. So you can take a second to think about what this program is going to print to the screen. Nice, your second is over. So let's see what's happening. We nest a bunch of things together. We go to the most deeply nested one. And it's just a print function which isn't doing anything because it is not being executed. It's passed as an argument to another print function. Now, what does a print function do with its argument? It prints it to the screen. Now, we know how we print text to the screen, but how do we print a function to the screen? Well, in Python, a function is an object, and objects have magic methods which describe how those objects should be converted into text representation. So basically this should print whatever text representation is assigned to the print object. Now after that we print the result of the previous print function. Now what is the result of a print function? Well, a print function shouldn't calculate any value for it, so it is not supposed to return anything. That's why we're getting none. So this should just print none. And that's what happens. Now, you may notice that for such a simple program, that's quite a complex explanation. But if you know how it works, most Python programs you read are going to be easy for you. Because no matter how clean code is or how much code there is, if you know that a function accepts arguments and returns value and are able to trace where that happens, you won't have any problem figuring out a complex code base. But still, many people get confused with this program, right? So let's take this example to Async.io. But before we do, let's talk about generators, because generators are very interesting in the sense that very few people understand generators, and there's a good reason for it. Half of Python community is devoted to web development, which is the part I'm mostly busy doing most of the time. And usually, when you go to a Python interview and a question about generators arises, this is how it goes. The interviewer asks, "What are generators?" And you say, "Well, generators are those functions where you use yields instead of returns." And the interviewer goes, "Okay, so why would you need such a function?" And you say, "Well, if we wanted to generate a sequence of numbers, we wouldn't have to store all the numbers in the list, taking up a lot of memory. We could just generate them one at a time, and this way our program would be more memory efficient." At this point, interviewer says, "Okay, great job, let's move on to the next question." But the result is, that's a very primitive understanding of generators. And there is a point because we don't generate sequences of numbers in web development every day. But the problem is, if you want to do Async I/O, you better understand the generator as well. So let's explore that a little bit. Let's say you have a sequence of numbers to generate. Let's say even numbers. So say you pass two values which define the bounds of your even numbers generated. And let's do it without generators. You create an empty list of numbers. If it's an even number, you append it to the list. Fair enough. Now let's see if our function works. And it does. Where the problem is that if you were to go a little bit beyond, you would have to wait until the numbers are printed out. But what if we do it using generators? So first of all, we remove this return statement, we remove this list, and we just add a yield here, right? You may notice that it doesn't work the way we're used to have it work. So what do? When we run this function, we get a generator object, which doesn't do much by itself. Similarly, if we execute an async function like that, we are going to get a coroutine, which is not going to run by itself. So what do? Well, let's assign this generator to a variable. So what can we do with a generator? Well, we can pass it to the next function. And this way, we are going to get the next consecutive value from this generator. So basically, we're moving on to the next yield using this loop. Now, you may notice that if we do this enough times, we are going to get an exception. So why is that? Well, if there are no more yields left to yield for a generator, it throws a stop iteration error. But fun thing is, if we loop over a generator, we don't see that exception. And if we do it like this, the numbers are being printed out from the beginning. So why is that? Well, that is because a for loop handles this exception for you. But for the sake of it, let's rewrite this program using a while loop. So let's say, while true, we are going to take the next number and print it. Now, if we do it like that, we'll reach a stop iteration exception. So let's handle that. And there's our program. Now, what if we wanted to have two of those? And say we want to generate numbers from the number 100 to 110. Now, one thing we could do is we could do something like this. So you may notice that if we do it like this, those generators are being ran at the same time. Interesting, huh? Problem is this program hangs. It hangs because here I forgot to break the loop. But the problem is, if we break the loop, this is a little bit dangerous, because if we have more generators, we might break before all generators complete. Maybe we break when the first raises stop iteration. So let's handle that quickly. Let's wrap it into a function, or let's call it loop. We're going to pass a bunch of generators in. Then here we are going to iterate over those generators, and we are going to try to get the next value. But we would also like to get rid of those generators that are completed. So we are going to delete those generators we do not need. Also, we have to check in this while loop if there are any generators remaining, and if not, we're going to end the loop. So let's see how that works. And that works perfectly. Our program executes and terminates. Now let's review how this works. So we create two generators, because it's important to understand it, because it gets confusing very quickly. So we create two of those generators, those are generator objects which we pass in a list. We start an infinite loop. We check if this list is not empty. If it's not empty, we go and run this for loop. If it's empty, we exit. So if it's not empty, we iterate over those generators. So in this case, we go to even numbers generator, which counts from 0 to 10. We try to get the next value from it. If everything's fine, we print it, which you can see here. And then we go to the next generator in the loop, which is this one, which counts from 100 to 110. We print the value, and then we go back to the start of the while loop. We check if there are any generators left. There are. We go to the for loop. We repeat this until the first generator hits stop iteration error. We delete the generator, go to the next one, print the value, delete the generator, go to the start of the while loop. There are no more generators. We return. And that's how it works. Now, what if we try to apply it to the example in the beginning? So instead of generating even numbers, we're gonna say hello, get rid of the arguments, print hello, import time, sleep for 1 second, print goodbye. Get rid of this and create two generator objects. Remember, we have to call those, because if we don't, this is just a function. This is a generator object. Refer to the example with print in the beginning. Now, jokes aside, let's run it and see how it goes. And we have exactly the same situation we had in the beginning. Now, this is unexpected. Oh, correct. This is not a generator. So let's put a yield here. And let's get rid of this print statement, because our generator doesn't yield any value. It yields a none. So you can see that now it starts to happen at the same time, which is interesting. Now let's just quickly recap what this yield is doing here, because this is the point where it might get just a little bit too confusing. So we go into this loop with those two generators. And what happens is we start looping over them. We get the first one. We execute next on it. So this function is being executed. We print hello. We reach a yield, and this is when this next function returns. So at this point, we go to the next generator, which is this one. We print hello, and we yield, and the next function returns. For loop finishes, we go back to the start of the while loop, we start the for loop again, and we try to execute next on this generator. Now this yield is finished, so we go to the sleep function, we sleep for 2 seconds, we print goodbye, and we raise a stop iteration error. This generator is deleted, we go back to the for loop, same thing happens for the second generator, and we go back to the start of the while loop, no generators are left, we terminate. And this is exactly how it works. But if you look closely, you may notice that those two hellos are printed instantly. Then we sleep for 2 seconds before goodbye, and then we sleep again for 2 seconds. And that's not what we want, because we want to sleep simultaneously. We want those two goodbyes to be printed at the same time. So how do we do it? Well, you see, this program is synchronous. and it executes sequentially, deterministically. So if we have this time.sleep, here this program has to sleep for 2 seconds. We can't get around that. So maybe we can implement our fake sleep. What if this loop would get a lot of yields here, which would yield chaotically for 2 seconds before we can resume again? Now that might be a fair solution. Let's say we have start time here, and then we create a loop which loops until 2 seconds pass. So we say if current time minus start is less than 2 seconds, then we are going to yield. And we may remove this one. So let's see what happens. 2 hellos are printed, 2 goodbyes are printed. Ladies and gentlemen, we just invented Async IO. Now let's just think about it. So we run the first generator, print hello, go here, start this loop, we yield, so we move on to the next generator. When the next generator does the same thing, we come back to the first one, we go to the next iteration of the loop. Now it happens very quickly. And this is false, because 2 seconds haven't passed yet. So we yield again. And then this happens until 2 seconds pass and first generator completes, then instantly we go to the next one. Now, this code can start getting a little bit messy, so let's make a sleep function for it. We say for how many seconds we want to sleep. We copy this code here. So what do? We say sleep for 2 seconds. We write a yield here. Because if we don't, this is not going to be a generator. We're going to get an error here. Actually, let's do just that. We get an error, non-type object is not an iterator, which is quite confusing. But this happens because we pass a normal function to next. Actually, no, we're not passing a normal function, because here we execute hello. Instead of yielding, we return none, because that's the default return in Python. So here we are passing 2 non-values. We try to run next on a non, and we get this beautiful little error. So let's not do that. Let's add a yield here and run the program. Now, it may seem like the program works, but you may notice we're not sleeping. That's not what we want. Now, that is happening because here we create a generator object and we yield it, so this is completed instantly. Basically, this function is not fired. Now, how do we do that? Because that's a valid behavior, right? So in Python, there is this yield from syntax. And basically, this means that we want to run next here, and we want to basically redirect whatever this function yields. And again, our program works. So what we do here is we invented Async IO. So let's maybe try it out with Async IO. Let's say we create a main function, which is a coroutine, and in this function, we replace our loop with async.io gather. And instead of having this stuff in a list, we're going to do it this way, because that's the way Async.io API is designed. We run our main function, we get rid of this loop, and if we run it, it works exactly the same way. So notice that here we are not passing coroutines. We are passing generators, which I don't think this is even supported by Async.io API. But since there's duck typing, which means if we can yield from it, then it's a coroutine. It works. Now, this is all beautiful, right? But there's one strange thing. We still have this very weird sleep here. So you may say, okay, we have a simple example to demonstrate how Async.io works. But what if we want to use some libraries we love? What if we want to use requests? What if we want to use database clients? Are we going to have to write our own database clients which specify at which points we may go ahead and run something else while we wait? And the answer is yes. And that's a big problem, right? If you want to do Async.io, you have to have libraries that support Async.io and explicitly say where we want to stop doing whatever we're doing and move on to another thing while we are waiting for results. So what if we do not want to do that? Well, there is a way. What if there was absolutely no way to implement sleeping in our own way? So we would go here and we would sleep for 2 seconds. We would get rid of this and we would get rid of Async.io. We would make a thread out of hello. Then we would make another thread. Then we would start those threads. Now you may notice that we get almost the same result. What's beautiful here is that we don't have to implement our own sleep function. So what's all this hype with Async.io? Why can't we just use threads? Now, the problem with threads is that threads have no idea when we actually want to wait for something. So what might happen, if we have a program that does a bunch of stuff here before sleep and a bunch of stuff here after sleep, we might switch to the next thread not while we are sleeping, but while we are doing something else. And the problem with threads in Python is that we have something called the GIL, which basically says, in Python, you cannot run multiple threads at the same time. So basically, Python has a bunch of those threads, and it switches at regular intervals between those threads. Now you may ask, why? What's the point of it? If we have 10 threads and we can only execute one at a time, why bother having 10 threads? Why can't we just write an asynchronous program without threads? It shouldn't be any faster, right? Well, not always, because look at this program. Even though only one thread is executed at a time, basically we switch between those all the time. But if we switch during the sleep function, basically we optimize it, right? Because we may switch between those two threads during those 2 seconds, but because we were switching, this sleep function got started in both threads at the same time. Maybe a better explanation would be a network request, right? If you send 5 network requests and wait for a response from each of them, that's long. But if you use threads and you switch between them and you run one thread at a time, you still are going to fire those 5 requests almost at the same time, right? They would be fired one after another, but you wouldn't wait for a response before you fire another request. And basically, threads in this example work like stupid coroutines which don't know what are the best places to switch execution to another coroutine, but they do it at specific intervals. So what should we use? Should we use threads? Should we use Snko? Well, it depends. And to demonstrate it, let's switch to some more complicated examples. So check this out. Let's say we want to run 4,000 of those hellos. Each one sleeps for 3 seconds. Now here we have an example with Async. What we are doing is we are creating 4,000 coroutines. Each coroutine just sleeps for 3 seconds, and we measure the time it takes to finish this program in a quite naive way. But let's see what happens. 4,000 coroutines we finish in 3 seconds. That's impressive. Now let's do it using threads. Very similar. Create 4,000 threads, start measuring, run all those threads, wait for all of those threads to finish. Easy peasy. We run the program. Takes a bit longer. Why? Well, you have to create those threads. And to create threads, you have to copy a little bit of memory between them. And those switches between threads, they take time. Now, in this case, everything is happening cooperatively. And it makes sense. We bothered to write a whole new sleep function. We would like to have a better performance. Now, we also have another way to run a bunch of things at the same time. And this another way is using processes. Now, there is a big difference between processing and threads. You can't execute a bunch of threads at the same time, but you can execute a bunch of processes at the same time. Why is that? Because in case of processes, we are actually going to run 4,000 Pythons at the same time. When we use threads, we run one Python interpreter, which has a bunch of threads to deal with. Here, we run 4,000 Python processes, which are all synchronous, but since there's a bunch of them, they're happening at the same time. Now let's see how well this program performs. And you may notice that it doesn't perform that well. Now, why is that, you may ask? Well, that's because we are running 4,000 Pythons on one system. It's heavy for this little PC. So this looks like a disaster, right? Let's terminate it. Question is, what's the point of having processes if they are so heavy and so slow? Well, let's look at a bunch of other examples. So instead of sleeping, we are going to send network requests. So let's go to Async. Here's what we are going to do. We are going to send 200 requests to Google. Sorry, Google, for doing this. In this example, I wanted to spin up my own server and do it on my own server. The problem with that is my server wouldn't handle 200 requests happening almost at the same time. So our measurements wouldn't be accurate. So basically we are DDoSing Google, but Google is smart. Google is going to notice we're doing that, and Google is going to just reject those requests quickly. But the speed of one such rejection is still an HTTP response. So it's still fine to test it, to test this program with such a network request. So let's see what happens. We create 200 coroutines. Each coroutine creates a session and sends a GET request to Google. Easy peasy. Let's see how it runs. Beautiful. We just sent 200 network requests in 1 second. Let's do it using threads. Again, same thing. 200 threads, 200 requests to Google. And you may notice that in case of Async, we're using a different library which supports Async. Running the example with threads takes 5 seconds. Still a good result. Now let's run 200 processes. And we're starting to get disappointed because the results are very similar to... Actually, we perform a bit better here. But notice that here I've been measuring this time when we already created 200 processes. So you may see that this process of creating processes is very time consuming and their execution is fairly quick. But still, it performed the worst of all, and Async was a clear winner here. But let's switch our examples up a little bit. So we are going to go and run another example. Up. Okay, so what we are doing here is we are going to have a coroutine which sleeps for 1 second and then decides to check if this number is prime. Now, this number is not prime. That's why this silly algorithm is going to take a long time to figure that out. Roughly 1 second. And we run 5 of those coroutines. Let's see how it performs. And it takes 7 seconds. So why is that? Well, what happens is those sleeps are happening simultaneously. But then we have a task. Sorry, not a task, we have a function. We have a function which is blocking. We are running some numbers through it. And on our computer, our CPU does that. So since only one thread is being executed, it happens sequentially. We can't just tell our CPU to somehow clone itself and count those prime numbers at the same time. So that's why Async.io has no possible way of optimizing this function. Now let's run it using threads. And you may notice that we have similar results. In fact, almost identical. So in this case, threads perform just as well as Async.io. Now, if we have a bunch of threads, why doesn't this happen quicker? Well, same thing. Here you can notice how this GIL actually works, because if we could execute those threads at the same time, then we could run those calculations in parallel, right? But we can't, because only one thread is happening at the same time. So actually here we are switching between different threads as they're doing this calculation, and that's just slowing us down. There's no point in that. So that's why we get a similar result. But let's do it with multiprocessing and run 5 processes. Now that happened in 3 seconds, and here we actually measured everything from creating those processes to executing them. So it happened much faster. It happened 2 times faster than everything else. And why is that? Well, here we have the sleep, which Async.io and threads deal with really nicely. Multiprocessing deals with it just as well, because even though we have 5 threads which all run this function, all of those 5 threads hit this sleep, and those 5 processes hit this sleep, and they wait together at the same time, and then they execute this function. Each process executes its own version of this function at the same time. So that's why we're getting such enormous speeds here. So what's better? Threads, multiprocessing, or Async.io? I guess by this point you know that it depends, right? But let me show you one more example. So what we would like to do in this case, let's go to Async.io. We are going to send 10 requests to Google. But before we do that, we run the prime number function. We send those 10 requests, we run this prime function again. And we use Async.io for that. Now here's what's happening. We run those functions sequentially to check if this number is prime. We run those requests almost at the same time, and then we run this function again sequentially. And it takes us 13 seconds. Let's do the same thing with threads. Now at this point, you may predict what the result is going to be, right? And results are roughly the same as they are for Async.io. A little bit longer than 13 seconds, which is expected, right? Now let's do it with processes. Now we may expect that processes are going to make this faster, right? We finish in 5 seconds. But here's the thing. What if we have to do it 500 times? Right? We know our machine is not going to cope with that as well. And here, but let's think of it, right? What are the strengths of Async I/O? Async I/O is really great if you have to wait for an input-output operation. Now, when is Async I/O not that great? When you have to execute a CPU-bound task. But that's something multiprocessing is really good at. So, here's one thing we could do. Why don't we just combine both of them? So here what we are going to do is we are going to execute 5 processes, but each process is going to have its own event loop, and each process is going to run this coroutine where it looks for a prime number, sends 10 requests, and then looks for a prime number again. Now you may notice that in case of the multiprocessing example before, what we did was we would run 5 processes here, but each process would have to send 10 requests sequentially. But what if each process had its own Async I/O and could send those 10 requests at the same time and then wait for results? Well, that's what we did here. And it gave us the best speed of all. Now, to be honest, this is not my idea. This idea is from talk by John Rees on Async I/O and multiprocessing. And he combines this stuff into, I believe, AIO multiprocessing library. I tried to use that library for this example, but somehow I didn't manage to get the speeds I got by just doing this manually without a library. I'm not sure if I wasn't doing something correct, but that's the thing here. I will show you one more example. Let's say we have a cat. Cats are great, right? So why don't we have one? Now, this cat can do a whole bunch of things. It can eat. It can have free time. And by free time, I mean sleep. Why do we have this function in the middle here? Why can't we just sleep if that's the only thing he does? Well, you will notice in a minute. So we have 5 synchronous cats, and we let each cat exist for a little bit. So what happens is one cat starts eating, gets some free time, sleeps, wakes up, eats. So it's slow. Basically, those cats take turns existing. Not nice, right? So let's say we wanted to optimize it. Well, we may create an async cat, right? We could say, okay, import async I/O, and please create those cats, and cat exists for cat in cats. Unpack this, and there we go, right? We could make this a coroutine. And now we have everything. Oh, right. We have to use gather for it. Okay, and we run it. It's still synchronous, but let's say that this sync cat comes from a library, which we can't edit. So our solution would be either to copy the library, make this stuff async, right? Or we could just create an async cat, which inherits the synchronous cat and switches things up a bit. But let's say that this have free time. Okay, switches things up a bit, right? So here we would await, have some free time. In have some free time, we would await sleep. We would make this a coroutine. We would copy the sleep function. And then we would await Async.io sleep. And then use this async cat instead of the sync cat. And we wouldn't touch the eat method because there's no way we could optimize it, right? So let's run it. And you may see that it's quite fast. All the cats go to sleep at the same time, all the cats wake up at the same time. But what if this have some free time function has a lot more code, right? And what if for some reason we can't modify it? For example, maybe this function uses some stuff from C, and the library is being compiled to C, so when you import it into Python, you don't have access to the source code of this function, you just know that it calls sleep. So can you make it call sleep, but for sleep to somehow underneath switch itself to a coroutine? That's the first idea I got, because I like to do weird stuff. But as much as I tried, I couldn't succeed at it. So what you could do is you would have to turn to our dear friend threads, which weren't performing the best, but remember those had an advantage because you didn't have to rewrite everything to Async.io to use the benefits of threads when it comes to I/O-bound tasks. So let's see how it plays out. In the exist method, we get the event loop and we use something called runInExecutor, and we pass the synchronous function to this executor. This none means that we are going to use the default executor, which is thread pool executor. In Async.io you also have the multiprocess executor, but in this case we want to optimize something that is not CPU bound, so thread executor would be a better option for us, right? And basically that's what we do. We do not touch any of those functions. We make this into a coroutine, and actually this is unnecessary. We make this into a coroutine. Let's say we inherit here, right? And let's see how it performs. It performs very similarly to the first Async.io example. So we basically managed to get around this problem without having to rewrite everything to Async.io, using threads in the spot where we can't use Async.io and using Async.io for the rest. And that's pretty cool. And what's cool about it is that we can take advantage of both Async, threading, and multiprocesses to solve different kinds of problems. And we don't have to use something exclusively, and we don't have to fight over what's better, because everything is better for different kinds of problems. Now, question is, where can you go from here? First of all, check out John Reese's talks on Async. Those are phenomenal. This is the Thinking Outside the Jill talk, where he discusses how we could take advantage of Async and multiprocessing. Also, from John Reese, we have a talk which is called What is a Coroutine Anyway? And in this talk, he explores how coroutines work underneath in depth. And it's also very, very, very informative. Next thing is check out Thinking About Concurrency. And this is a talk by Raymond Hettinger. There are two versions of it. Both are amazing. Basically, he explains the idea I explained, or better say, I just explained what he explained. Now, one other thing with Async is its API is changing rapidly. So watching talks made by core developers of Async, where they discuss changes to the API and what they plan to change, or what they think is was a bad design in the past but maybe a better design in the future, is also very, very helpful. I can also recommend this talk by Andrew Svetlov. He's also a core developer, and he explores some of the things you shouldn't do in Async, and this information is also a goldmine, because some of the points he makes I couldn't find anywhere else. And one another talk recommend with all of my heart is Łukasz Langa's Async and Music, which he did on the previous code dive, and that talk is phenomenal because he shows you a completely different take on Async and shows you what you can do with Async apart from sending network requests at the same time. So he just controls MIDI synthesizers from his code simultaneously using Async. So that's amazing. Now, thanks a lot for sticking with me for this talk. Let me know what you liked, what you didn't like, and what I could do better. Definitely, if you're interested in the topic, check out the talks I showed in the end. And have fun at Code Dive. See you very soon, probably in a year, not sure about that, but you can still find me by the links in the description, chat, and see you soon. Thanks for your attention, and thanks for sticking around.
Oleksii, thank you very much. Great presentation. This is Code Dive. Don't go away. We're going to take a short break, but stay tuned for more.